If I calculate gamma from that prior equation, I can then say the value of the option is the risky return present value of the real-world payoff. So notice now I'm using a real-world probability P to get my expected payoff, and I'm using a risky return gamma to discount it. They're consistent. So this would be the price. And what I now want to show is that with a little bit of algebra, this price is exactly the same as the risk-neutral price, where I use P star for the probability inside the bracket, and I use R for the discount rate. So we just need to do a little bit of algebra, which I'll go through quickly, and you can confirm this. So in order to derive that the price using the risky return and the real-world probability is the same as the earlier risk-neutral probability, let's do some algebra. So first of all, we have an expression for the discount rate at the risky return. Secondly, we know that this is now, notice this is P star. We can express the risk-neutral expected value of the option payoffs in terms of the price of the option with risk-free interest. The final step is to note that we can write the real-world probability, the real-world expected payoff, as the risk-neutral expected payoff plus an extra term. This risk-neutral expected payoff now becomes this by the prior slide, and then I recall the formula for delta. It's Cu minus Cd over U minus D. It's called delta S. So what I now, if I pull these pieces together, I get that C, the price using the risky return, is the risky present value of the real-world expected payoff. Do all the algebra, and lo and behold, I get the original price, delta S plus P. In other words, the P price, the real-world price with the gamma return, is the same as the P star price, the risk-neutral, with the risk-free return. And again, this is an algebraic exercise that assumes that somehow we knew what delta of the option was and what the T-bill position was, and but it cannot be used in practice unless one first prices the option. So if you price the option, you are then able to go back and reprice it in a risky world. But you can't derive the price of the option in the first place using this methodology. So a couple of comments. One is that we may not know the correct value of alpha. And alpha was the stock return, the risky return. And the point is, what this is saying is that the model is internally consistent. If you start off with any value of U and D, then as I mentioned earlier, P, the real-world probability of U, and alpha are a pair. They're a pair in that any alpha gives me a P that works, any P gives me an alpha that works. So we can think of, even though we may not know the unique alpha, this derivation says pick any alpha you want, and P will be determined by that. And then when you go through all the steps, that P and that alpha will give you a different gamma, but nonetheless, when you're done, the pricing of that option will be the same as the risk-neutral price.